Hey everyone, and welcome back to The Explainer. Today, we're diving into an absolutely crucial foundational chapter in programming, Python's flow of control. We're finally moving way beyond those simple top-to-bottom scripts to explore the real architecture of dynamic code. How it routes logic, makes decisions, and automates all that boring, repetitive stuff. Let's get right into it. Okay, so here's our roadmap for today. First, the flow of control. Second, making choices with selection. Third, the rule of indentation. Fourth, repeating tasks with iteration. And finally, number 5, the range and while loops. All right, section 1, the flow of control. So what exactly is the flow of control? Well, by default, Python reads your script kind of like a book. Top to bottom, line by line, and an exact sequence. That order of execution, that's your flow of control. But let's be real. Real-world logic rarely travels in a perfectly straight line, right? That means our code needs different structural architectures to handle varying conditions. So Python actually routes these pathways using 2 main types of control structures, selection and repetition. To really wrap our heads around these structures, let's think about 3 real-world analogies. First up, sequence. Think of this like a school bus on a single road. The driver has literally no choice but to follow the path, hitting one milestone after another. Next, selection. Imagine you're holding a $10 bill at a stationery shop. There are dozens of pens you could buy, but you have to select just one path based on your exact preference. And finally, iteration, or repetition. This is perfectly represented by a butterfly's life cycle. Eggs, caterpillar, pupa, butterfly, and then right back to eggs again. It's a continuous, repeating loop. Moving on to section 2, making choices with selection. And this brilliantly illustrates how binary decisions actually work in Python. Imagine we're checking if someone is eligible to vote using an if-else statement. Following the path for an age of 18 or older, if that condition evaluates to true, control routes one way, executing the code that lets them vote. But if we look at the alternative path, say the condition is false because they're under 18, control guarantees a totally different outcome, blocking the action. It's a strict binary fork in the road, based entirely on the data it evaluated. Let's actually trace this logic together. Notice that decision diamond right there in the center? Let's say we want the difference between 2 numbers to always be positive. Our program routes the data through a really simple question. Is number 1 greater than number 2? If the answer is yes, it branches right, subtracting number 2 from number 1. But if no, it branches left, subtracting number 1 from number 2. Because of this selection structure, our code dynamically adapts to any input to guarantee we get that absolute positive difference. Pretty cool, right? So to build this kind of architecture, Python gives us 3 main tools. The foundational if statement checks a single condition. If it's true, it runs. If it's false, it just skips it entirely. Then we have the if-else statement, which provides 2 distinct alternative paths. But what about really complex routing? Say, building a calculator that evaluates plus, minus, multiply, or divide. For that, we use if, elif, else. Elif, short for else if, allows us to chain multiple conditions together sequentially. The interpreter checks each one by one, until it hits a true condition, and then it executes only that specific block. All right, let's take a quick detour into section 3, the rule of indentation. Now, before we jump into loops, we have to talk about a formatting rule that is absolutely crucial in Python. Check out this quote from Python's creator, Guido van Rossum. He said, "Don't you hate code that's not properly indented? Making it part of the syntax guarantees that all code is properly indented." In most other languages, you use curly brackets to group your code, and indentation is, well, mostly just a polite suggestion to make things readable. But Python took a much stricter approach. In Python, those spaces or tabs at the beginning of a line, that leading white space, are actually a literal part of the language's syntax. The exact same level of indentation firmly associates statements into a single strict block of code. So when you write an if statement, everything you want to execute under that condition must be indented beneath it. And here's the kicker. If your spaces or tabs are off, your program doesn't just look messy. The interpreter will literally throw a syntax error and refuse to run. It's a design choice that forcefully mandates clean, readable habits. Okay, section 4, repeating tasks with iteration. Now, let me pose a problem to you. What if you were tasked with printing the first 100,000 natural numbers? Think about that. If we rely solely on sequence, that strict top-to-bottom execution we talked about earlier, you would literally have to write print statements all the way down. I mean, 100,000? Writing out that many consecutive print statements isn't just tedious, it's honestly a programming sin. It's horribly inefficient and incredibly brittle. We want the machine to do the heavy lifting for us, which brings us squarely to looping constructs. So let's see how this builds out. We can create a loop using 4 simple logical steps. Step 1. Initialize a control variable. Let's call it count and set it to 1. Step 2. Perform the action, which in this case is printing that value. Step 3. Increment the variable, so increasing our count by 1. And step 4. Set a logical condition to repeat steps 2 and 3 as long as our count is less than or equal to 100,000. These 4 parameters are the secret sauce. They allow us to automate massive repetitive tasks with total elegance and precision. Which brings us to our final part, Section 5, the range and while loops. Let's trace the execution path of the for loop right here. This is designed to iterate over a known sequence or a very specific range of values. The loop starts up and immediately asks, hey, is there an item left in our sequence? If yes, it executes the statements inside the body and then cycles right back up to grab the next item. It continuously repeats this circuit until every single item is exhausted. Once that final item is processed, the loop elegantly terminates and hands control over to the next part of the program. Now, to actually feed that for loop its sequence, we usually use Python's built-in range function. Range takes up to 3 parameters: start, stop, and step. If you just call range 10, it generates a sequence from 0 up to but not including 10. But when you define the step, you're really controlling the engine. You could generate a sequence of numbers decreasing by 1, or maybe jumping by multiples of 10. It supplies exactly the sequence your for loop needs to traverse. Now let's contrast the for loop with the while loop. A while loop is totally different because it isn't based on a preset range. Instead, it executes a block of code repeatedly as long as its control condition remains true. And crucially, it tests this condition before every single iteration. If the condition evaluates to true, the loop body runs. But if the condition is false right from the very initial check, the entire body of the loop is bypassed completely. It never executes, not even once. But, all this power comes with massive responsibility. So what actually happens if your loop's condition never becomes false? Say, what if you just forget to increment your count variable in step 3? Well, you've accidentally created an infinite loop. Your program will literally be trapped in that cycle forever, or at least until it crashes or you force it to terminate. It's a classic logical error and honestly a great reminder. When you give your code the power to make choices and repeat tasks, you have to be absolutely precise with your instructions. Check those exit conditions, folks. Thanks so much for joining me on this explainer, and I'll catch you next time.